Okay, this one's all about similarity. You thought we were probably done with similarity, but no, it comes back when we talk about area and stuff. Volume and surface area of similar solids. So there's some rules that happen that are different when you have to deal with similarity in 2 and 3 dimensions that are kind of different than one dimension. Kind of everything we've done before has been how lengths change when figures are similar. Now we're going to be talking about areas and volumes. Okay, so here's the theorem right off the bat. Notice one of these is from chapter 11, one of these is chapter 12, because one's about surface area, one's about volume. But right off the bat, we have if you have two polygons, and we can read this stuff here about remind you what we mean about similar figures. But yeah, right off the bat, if these two figures are similar, they're similar with, usually we say scale factor k. And I'll say it this way, linearly similar, like, if this is 5, this is 10, k would be 2, that type of thing. If the scale factor, the multiplier between linear things is k, the area scale factor is going to be k squared, and that's the whole point of this theorem right here. We'll get into the examples, and then we're going to talk about that in terms of volume. The volume, okay, here we go. Scale factor 2 to 3. That means like linear. We would call that k. I have this example right here. The surface area, any kind of area, is going to be k squared, but the volume, lo and behold, is k cubed. And there's a pretty easy way to see why that's true. Do I have some room somewhere? I just want some room. Yeah, and they word it here again. I'm going to come back to this example in a second, but just to give you a really, I don't know, kind of a basic example. If we have a 2x3 rectangle, and we scale it up with a scale factor, let's say 2, each side is going to get doubled, right? So if we multiply each side by 2, that length is going to become 4, that length is going to become 6. Let's think about what happens to the area. This area is 6, this area is going to be 24. So it's not just, 6 times 2, it's 6 times k squared. We have to multiply that by k squared. If there were a volume involved, well, let's just say this is a box and it's a depth of 1. That now has a depth of 2. The volume of this, so this is kind of an old story now, but that was the case at the time. The volume here is 6. The volume over here, let's multiply it and figure it out first. This is going to be 48. Notice that's being multiplied by 8. That's being multiplied by k cubed. Okay, so it's a simple thing to kind of demonstrate, but the way they're going to have you apply it is going to be a little more advanced than that. All right, let's do this stuffed animals thing. What's weird about the stuffed animals is we don't have a formula for that. Like this, I could find the surface area and the volume and things. But what if it's just any old figure? So yeah, the similarity is going to help us convert from one to the next, or kind of figure out one based on a similar figure. Yeah, so I'm going to pretend we have a stuffed animal. There we go. And can I copy paste and make this thing bigger? The bigger one, we have a teddy bear, looks kind of demented. They're supposed to be similar. The bigger one has a height of 16. The smaller one has a height of 12, but they are similar. So right away, with the 16 and the 12, I can figure out that the ratio of 16 to 12 is that 4 to 3. Yeah, it's 4 to 3. Since those are ratios of heights, I'm going to call that linear, a linear kind of measurement ratio. I'll think of that as k. If that's how linear things kind of talk to each other, that ratio will be known as k. And then, of course, surface area will be k squared, and volumes will talk to each other as k cubed. If the smaller one needs 40 square inches of material, so that's basically telling us that the surface area of whatever part of this that this is covering is 40, then the surface area of this one is what I'm trying to figure out. Well, this one over here, this stuff's kind of in the way. What I need to multiply this surface area to get to this surface area, I have to multiply that by k squared. So I need to take 40 times 4/3 squared to figure out this new thing. 4 thirds squared, of course, is 16 ninths. And 40 times 16 ninths is 640 ninths, which is a weird number, but it's perfectly good for a surface area, 71.1. And this is what, centimeters? No, inches. This is square inches of material, because that is a square measurement, area measurement. Page it was, okay. Great, just making sure. Okay. Was that it? All right, so let's determine if these things are similar. You know what? This is really not the most important thing we do this unit, honestly. For determining whether things are similar, the only thing we'd have to go on would be that every single length has to be in the same ratio, and all the angles have to be congruent. So if we're supposed to assume that these are right triangular prisms, can I figure out that like triangle by triangle, we have rules for that, right? Like we did triangle similar to triangle back in that whole triangle similarity unit. Yeah, all these have been multiplied by 1.5. All those lengths have been multiplied by 1.5. So we have side, side, side on the base. K equals 1.5. And if that 1.5 ratio seems to hold with everything, and it does, it seems to hold with everything. So also K is 1.5. So I'm just going to say yes. It's like by side, 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 side. We have, or actually it's 9 sides. All 9 sides are in the same ratio. And if we're led to believe that they are both right prisms, then all the angles would be the same. So I'm kind of going fast with that one because that is not a central concept. Determining if things are similar is really not a central concept of this unit. Given that these are similar, find the length of the side corresponding to the 7. Okay, so find x if I know these things are similar. Okay, this is where it gets a little bit more interesting. I know I can compare things. I know this thing and this thing are on the same kind of channel, like they're both areas. So I could, if I divide them, and I'm in the habit of always doing big over little. It doesn't really matter, but you'll see me always do big over little because it provides some consistency. This value of k is not just k by itself. This is k squared. I know that's the ratio of k squared because I'm comparing area to area. 72 over 50 can be reduced. It's also the same as 36 over 25, which is lovely because it happens to be 6 over 5 squared. So that tells me that k is just 6 over 5. And so that's the ratio of how these things talk to each other. So x is 6/5 bigger than 7. So to find x, I just have to take 7 times the ratio of 6/5, and I get 42/5, which I believe is 8.4. Just checking that. Yeah. Okay. Diagonal of a cube is blah. Diagonal of another cube is blah. The larger cube has a volume of blah. I'm going to do this in class. We'll do that as the warm-up. The base areas of two similar... this is it. Oh my gosh. The base areas of two similar prisms are that and that. Find the ratio of their length and the volume of the larger prism if the volume of the smaller prism is 150. You know what? I'd really like to show you... after this is over, I'm going to show you cube rooting on your calculator. Okay, so I'll do this one. It's fine. Two similar prisms. Well, the thing is, I have no idea what these prisms are. These could be triangles. They could be quadrilaterals. They could be funky, non-convex, oblique things. Like, I have no idea what this thing actually looks like. That's a really weird thing. But then I have another one. Oh, there's a big one. I'll make a little one. I kind of made this weird, really hard to draw shape. It looks like a block of cheese. Okay, so the base areas. Base area here is 200. Base area here is 32. Those are areas. So those are square things. So when I divide those and I find this ratio, the ratio that I'm finding is k squared. Does that reduce nicely? 200 over 32. Oh, good. That's the same as 25 over 4, which just so happens to be 5 halves squared. So I know already that 5 halves, 5 over 2, happens to be k. Find the ratio of their lengths, which I did. That's this. And the volume of the larger prism, if the volume of the smaller one is 150. I'm trying to find this volume. Well, to multiply from this volume to this volume, I don't multiply by k. I don't multiply by k squared. I multiply by k cubed. So I need to take 150 times k cubed to get this big volume. That's my big V for big volume. This is 150 times 125 over 8. 150 times 125 over 8. I get something like 9375. Oh my gosh. 93. Okay, that's really bad. 9375 over 4, which as a decimal is 2343.75. Okay, just real quickly, I don't know how any room here. There might be a time on your calculator where you have to, or when you're doing one of these things, where they give you a volume and they divide by another volume. Like say in this last problem, if they hadn't given us those two base areas or something, they gave us volumes. So if you're starting off with volumes, you're going to divide volume by volume and you're going to find k cubed. And then later in the problem, it's not unlikely, or it's not probably hard to imagine, you might have to find k, or you might have to find k squared. So what's going to happen? So let's pretend we have a volume 1 of like, I don't know, say it's a big volume, 1500, and the volume of the smaller one is something, I'm just making this up, it'd say something like 625. I hope this might work out nice. I don't know. That's k cubed. And I'm supposed to try to figure out what k is. Well, what you have to do is you have to find the cube root of this big nasty fraction. So I just want to show you on your calculator what that is. And you can't see it from here. But the menu command for this whole thing is you have to do second, and then you have to press the button that looks like the little caret button, the little exponent button. So it's like second exponent, and that gives you a format for entering something like this. Just so you know, so if you found it correctly, I'm going to go control, that little caret button, I push a 3 there for the outside of the thing, and I made up this fraction, 1500 divided by 625. If I find this as a decimal, just to see if you want to check it and make sure you did it right, this decimal should turn out to be 1.339 if I round to 3 places. Now we'll see if we can do that in class. Okay, that's it. I'm going to stop there.